In our previous lecture we were discussing about the statistical averaging of the fluid flow equations to model the phenomenon of turbulence, and we eventually came up to a conclusion that it is giving rise to a problem of closure. That means you are getting some extra quantities known as the so called Reynolds stress, but there are no obvious expressions by which you may evaluate the Reynolds stresses. Therefore, one has to model it by some physical intuition or physical understanding, and the model may be as good as your physical understanding, and it is not so trivial or not so obvious to come up with a very accurate or a very correct model, and that is why in terms of understanding the statistics of turbulence it is still an unsolved problem. So what we will like to see is not that what has been the most recent advancement on these topics, because those are mathematically very involved, but we will look into some of the basic physical features, or so to say some of the most primitive models, but for most of the physicists the most primitive models were the best ones, because they could give the most important physical insight on the turbulent stresses or the Reynolds stresses. But before going into that, let us just recapitulate that how the different length scales are involved in the process of turbulence. So we were talking about, in our initial discussion of turbulence, we were talking about the concept of energy cascading, and let us just revisit it. Just let us try to say that we take an example. We are not talking in terms of example of a turbulent flow, but let us say that you have two plates. In between the two plates you have a big piece of stone. Okay, so this is not flow, this is just analogy. Now what you try to do, you try to apply a relative shear between these two plates. When the shear becomes very strong, this may break up into small pieces. So as if it is extracting some sort of energy from this shear mechanism and getting broken into maybe smaller granules, and these smaller granules, when they are, the entire thing is under shear, so as if it is a crushing machine, and in that way this is getting broken into smaller and smaller pieces continuously till it comes to really smallest of the granules, and energy as if has passed from this shear by shear mechanism from the largest scale to the smallest of the granules. How it has passed? It has passed through the energy cascading mechanism. Equivalent to that also something is happening in this particular hypothetical example. So what is happening in a turbulent flow? This large piece of stone is like a large fluid mass. It is extracting energy from the mean flow. So turbulent flows are often characterized with high Reynolds number, and that is why it can have a high mean kinetic energy, so that the large eddies can continuously extract the kinetic energy from the mean flow and sustain their rotationality. So always the question is that when the large eddy passes on its energy to the smaller eddy, then how does the large eddy itself sustain? It sustains because it continuously extracts energy from the mean flow and it passes it on to the smaller eddies, that again passes it on to the smaller eddies. So it is a continuous process, it is not that the process is stopped at once, and that is how energy is passed on from larger to smaller length scales. Eventually when it goes to the length scale where viscous effects are very important, then this entire energy is dissipated in terms of viscous dissipation, and that is how sort of it is a cycle where energy is taken from the flow and energy is sort of dissipated by viscous action, and this cycle goes on. So one important understanding from this cascading mechanism is that in a turbulent flow interaction between eddies is very important, and interaction between eddies makes the exchange of momentum fluctuation, energy fluctuation, all these things. Therefore we must have a sort of at least an overall idea of how you have the exchange of momentum because of fluctuating components between several eddies, or maybe two eddies taken at a time. And what Prandtl did is, Prandtl tried to draw an analogy between this and the exchange of momentum between molecules, and that is how he appealed to the kinetic theory of gases, which was substantially developed at that time when Prandtl started looking into the problem of turbulence. So what was the whole idea? The whole idea is that if you have two molecules, you know that there may be a characteristic change in the velocity of a molecule when one molecule traverses a threshold distance which is like say a mean free path and collides with another molecule, because the smallest resolution that you can think of in terms of a molecular characteristic length scale is the mean free path, because the change in characteristics of a system of molecules may be possible only with collision, and collision can take place only after a mean free path is traversed. So in terms of a molecular length scale, the mean free path is the characteristic length scale over which one molecule will go and interact and have a change. So if there is a difference delta u between the velocities of these two molecules, and let us say that this distance is this coordinate direction is y, then this delta u is approximately as good as the gradient in u times the length, right. This is the molecular picture. Now in turbulent flow the molecular picture is not important, it is just the analogy that we are drawing. Now imagine that instead of these molecules we are having interacting eddies which are lumps of masses with some sort of rotationality, some sort of vorticity. So in a turbulent flow basically what happens, there is a chaotic advection of vorticity with respect to position and time. So it's like the vorticity is one of the very important issues in turbulence. So these are strongly rotating structures. Now whatever it is, these have fluctuations in their random fluctuations in their velocities, just like they have u prime, v prime, w prime, like that. So what happens if you have say one eddy interacting with another eddy? So we have to find out one such gradient and one such length scale. So the question is, what is the gradient? That may be straightforward, because on a statistically average sense we are only keeping track of the average quantities. So the average quantities when we are keeping track of, maybe we describe the gradient in terms of the average. So instead of the gradient in the velocity as we had for the molecular picture, here we are talking about the gradient in the average velocity, because anything beyond that is taken care of by the fluctuation, which statistically gives rise to the interaction between eddies, but average of the fluctuation is 0 itself. Now if you want to see that what is the relative fluctuation between these two, so that is analogous to this delta u. So let us say that is u prime. So when you are describing u prime approximately say, or the scale of u prime, you have this one, you have to multiply this with a length scale, just as you did for the molecular picture, the mean free path. Here you do not have an obvious mean free path type of a concept, but if you think of an equivalent length over which maybe one eddy has interacted with another, then that equivalent length Prandtl introduced as Lm, and he called it as mixing length. We should always keep in mind that a good work of physics is not always that you may represent exactly the reality, but create a sort of a picture, physical picture, and try to develop maybe a sort of simplistic mathematics to represent an equivalent reality, and that is what Prandtl tried to do. Not that this is what exactly happens in a turbulent flow, but he tried to have a sort of a qualitative picture which is represented by the simple quantification. Again, this is very simplistic, because Prandtl never had a clue, in fact till now there is no clue that exactly how this varies. I mean there are again approximations, but it is not as straightforward or as obvious as a molecular mean free path for flow of gas molecules. Now why this type of quantification was important? Because eventually Prandtl wanted to model the Reynolds stress term, that is minus rho u prime v prime as an example with an average. So we could see that this is an extra equivalent term of the same dimension as that of stress, which came into the picture because of the averaging of the Reynolds averaging of the Navier-Stokes equations. And since these are not known quantities, it gives rise to a tensor with 6 unknowns. He had a desperate attempt of writing it in terms of some equivalent quantity which sort of is a pseudo known. So you have this u prime, and what Prandtl said or hypothesized that in terms of order of magnitude u prime and v prime, the fluctuations should be equivalent, and then this thing in terms of an order of, see, it is an attempt of writing it in terms of a scale, not really, because you are not really knowing that what is this correct length. So it is just a scale, but exact value is not known properly. So then it boils down to the form of rho just the square of this, but this form I mean in terms of its in terms of the constituents of the equation as a form it is fine, but we have not given any due consideration to the algebraic sign of this. So we have to give a consideration to the algebraic sign of this. Remember, at the end we want to write this term eventually as some equivalent viscosity, turbulent viscosity we called it, into the rate of deformation. We are just taking a 2-dimensional example where you have fluctuation components u prime v prime. Now if you want to do that, then the obvious way should be that, and one of the things we concluded is that this mu t has to be positive. So if it has to be positive, instead of writing it in this way, it is better to write in the following way. Because then it is quite clear that this part of the expression you are assuring to be positive. See, this is just an analogy between terms, and therefore it is important to preserve the physical sense. We discussed earlier in our previous lecture that u prime and v prime are correlated in such a way that in a isotropic turbulence case you have their average product of the average 0, but anisotropic, a positive u prime will be associated with a negative v prime and the other way. So that minus effect will be adjusted with this minus effect, so that eventually you should get a positive mu tau if you mu t if you have a positive du dy. So what it means is that, so we discussed that example with a positive du dy, with a negative du dy it will just be the opposite one, but whatever is the example with a positive du dy, that gives us a clue that if du dy has to be positive and the entire term has to be positive, that means mu t has to be positive. It is the other way, that if du dy is negative, then this term will be negative, but still mu t has to be positive. So the positivity of mu t is what has to be preserved, and that may be preserved by writing this term in this way. So this becomes the mu t. Turbulent viscosity, sometimes it is also called as eddy viscosity, mu e, and the name is very clear because it is because of the interaction between fluctuating components of eddies, fluctuating velocity components of eddies, that is why it is often called as eddy viscosity. So the summary of Prandtl's initial work is that mu t, or the eddy viscosity, Prandtl said that this is related in this way. Sometimes sort of a kinematic eddy viscosity is also considered, that is you divide mu t with the rho. So that is written as a nu t, that is mu t by rho. What kind of insight Prandtl's hypothesis could give us? Let us try to make an assessment. First of all, we have to realize that this is a simplification, and one must confess that this is actually a huge amount of oversimplification. Despite that oversimplification, it gives us some remarkable understandings, and one such understanding is that how the velocity varies very close to the wall in a turbulent flow. So, we will now try to develop a sort of physical picture of the velocity variation close to the wall in a turbulent flow. So, near wall velocity variations. We will look it from different angles, but first the angle from which we will consider would be a sort of a follow up of the Prandtl's mixing length model. So, this is Prandtl's mixing length model. This LM. So, when we talk about the near wall velocity variations, we have to keep certain things in mind. The first thing is that no matter whether the flow is turbulent wherever, but very close to the wall, it is always laminar. So, the turbulent structures are important as you go little bit away from the wall, but adhering to the wall, because walls are excellent dampeners. So, adhering to the wall, and if you look into the picture of the flow close to the wall, we will see that what is that thickness what we are talking about as adhering to the wall. When you say adhering to the wall, it is very qualitative, but we will come to its quantification slowly, but at least we should recognize that very close to the wall over a very thin layer, how very thin it is, we will see that the flow will be always dictated by a laminar behavior. So, turbulent flow does not mean that it is globally having the same picture. Very close to the wall, it is having a sort of a different picture. That is the first thing. The second thing is that when we are talking about region very close to the wall, we should also be bothered about the roughness of the wall, because in a region very close to the wall, the roughness elements of the wall interact very significantly with the flow. So, the question is how smooth the wall is, because if the walls are rough, there are protrusions from the wall into the flow, and those may disturb the flow. In reality, those are some of the triggering mechanisms of turbulence. So, we have to understand that what is the effect of the roughness, but first we isolate the effect of the roughness and assume that we are having a sort of a smooth wall. So, if you are having a sort of a smooth wall, let us see that what are the important velocity scales and important length scales very close to the wall. So, let us say that you have a smooth wall. Let us try to draw a physical picture that you have a wall, fluid flow is taking place over it, the coordinate normal to the wall into the fluid is y. So, very close to the wall, where say the effects are virtually laminar. Now, at the wall itself you can calculate a wall shear stress, right. So, wall shear stress gives a sort of a picture at the wall, and since that is exactly at the wall, no doubt that it has to be driven by laminar behavior, because wall shear stress is calculated exactly by velocity gradients at the wall. Calculating that for a turbulent flow is difficult, because that slightly away from the wall is still affected by turbulent fluctuations. So, it is not so easy to measure it, but if it is accurately measured, then this is one of the important parameters that we can get from the wall, and just from the scaling arguments, tau wall is given by some rho into u square, it is just from the dimensional analogy. So, if you know what is tau wall, then whatever u that you get, let us call it u tau, that is a correct velocity scale very close to the wall, because that velocity is derived from the wall shear stress. Okay. So, we come up with a velocity scale very close to the wall as u tau, that is tau wall by rho to the power of half. Next, length scale. So, what is the important length scale? So, close to the wall, if it is a smooth wall, the wall roughness may be an important length scale, may not be an important length scale, but if it is a rough wall then the wall roughness itself may be an important length scale. But here since wall roughness does not come into the picture, we are having a length scale that is solely dictated by the physical mechanism within the fluid, and very close to the wall whatever is happening is a sort of a effect of energy cascading from the large eddies to the very small eddies. So small eddies we have also discussed it earlier that large eddies have lot of anisotropy, but small eddies have virtual isotropy, but large eddies are not perfect, small eddies are not perfectly isotropic, but they have greater isotropy than that of the large eddies. Not only that, small eddies are having certain important characteristics, sometimes they appear in patches and disappear. So these are known as intermittency in turbulent flows, and very involved concepts are related to this. But whatever we get as a gross understanding from the behavior of the small scales is that as you go to the smaller eddies and these things are dissipated, it is the viscosity that dominates the mechanism, and more importantly the kinematic viscosity. So if you want to find out what is the important length scale that is dictating that, then the length scale over that should be the kinematic viscosity divided by this velocity scale. Just you look into the units, this is like meter square per second, this is meter per second. Okay. So correct length scale is given by the, is governed by the kinematic viscosity, because in the small scale the dissipations become more and more important, and so this is very close to the wall. Not only that, very close to the wall we may have a sort of a simplified physical picture. What is the simplified physical picture? The simplified physical picture is that if you are say focusing your attention on a very small region close to the wall and trying to draw the velocity profile. Velocity profile means mean velocity profile, so because we are talking about the statistical quantities. So the mean velocity profile very close to the wall will just be linear, and the reason is straightforward, because you are really considering a very short length over which you are considering the velocity variation. That means a linear velocity profile will mean that the wall shear stress is a constant, because tau wall is like locally mu du dy. So if u varies linearly with y, du dy is like a constant. So if we calculate tau wall over that very thin layer, then that tau wall will be just mu into u by y. This is where u profile is linear, very close to the wall or adjacent to the wall. Okay. So when you have this wall shear stress and the related expression, now let us try to write the velocities and the lengths non-dimensionalized in terms of the velocity and the length scale that we are talking about. So we introduce the non-dimensional velocity. So we introduce some non-dimensional velocity, say u plus, which is u average divided by u tau. This is a non-dimensional velocity. So this is the scale. Always you non-dimensionalize with the proper physical scale, because the scale gives what? Scale gives the maximum value. So that is, you expect this to vary between 0 to 1. When it is maximum it is 1, minimum it is 0, and y plus as y by y scale. Okay. So these are two important non-dimensional quantities that we introduce. So let us write this wall shear stress in terms of these quantities. So we will write tau wall equal to mu, in place of u bar we will write u plus over u tau, in place of y we will write u plus into u tau, sorry, in place of y, y plus into y tau. Y tau is like this L tau, this is as good as y tau. So since we are using the y coordinate, we are just calling it y tau. This is the characteristic length scale. It because of the apparent isotropy, it is y or x or whatever, it is just the length scale that is important, not the directionality so much, but close to the wall the directionality is important because the normal gradient gives rise to the shear stress. So when you have this one, now you may write u tau as a function of y tau. So y tau is what? Nu by u tau. So replace y tau with, replace this with nu by u tau, and mu by nu is the rho. So you have right hand side rho into u tau square, left hand side tau wall, and tau wall scale is rho into u tau square. So this gives u plus equal to y plus. Okay. Now this is like a sort of non-dimensional way of writing the velocity profile very close to the wall. If you go a little bit away from the wall, u plus may not be exactly equal to y plus, but over some distance u plus will be some function of y plus. That function is a linear function very close to the wall, it may deviate from the linear function a little bit away from the wall. There will be some region away from the wall when this will not work at all and a different form of the functional relationship will come. So we will try to look into that, what is that different form of the functional relationship, and for that we will appeal to the Prandtl's mixing length. So when we appeal to the Prandtl's mixing length, we will keep in mind that we are now not talking about a region which is really infinitesimally adhering to the wall, but slightly away from the wall, and because the turbulent effects are more and more important as you go more and more away from the wall. Slightly away from the wall, see if you go, it may be an interesting transition, because if you go further and further away from the wall, the turbulence effects are important. If you are very close to the wall, adjacent to the wall, the wall shear stress is the dominating factor. So that is the laminar effect that is important. So this we may qualitatively call as sort of inner region and outer region. So inner region is like a region very close to the wall, outer region is somewhat away from the wall where the turbulence effects are more and more important. But these regions are fuzzy, so there is a transition and it is a sort of overlap. So wherever there is a transition, these effects are, one effect is almost taking over the other. So if you have the total stress at the wall was solely due to the wall shear stress because of the laminar effects, and the turbulent stress was negligible or tending to 0, that is the minus rho u prime v prime average was 0. As you go somewhat away from the wall, you will find a threshold location where the wall shear stress effect is not directly there, except that it has got the effect of the wall has got propagated to the inside because of the molecular viscosity, but in terms of the turbulent stress is the solely dominating factor because fluctuations become more and more as you go close to the wall. So at that threshold limit, you can say that whatever wall shear stress was there, that wall shear stress has been transmitted to a layer where the value of the stress is now being dominated by the turbulent fluctuations. So at that overlap or transition, whatever is true is this type of a relationship, this one. So this we are writing for a sort of a transition from the wall dominated behavior to the turbulent fluctuation dominated behavior, and it is as if the same momentum flux is being transmitted across those two layers of the transition. That is what is the physical understanding behind this equation. So writing an equation is not important. See this, therefore this is not a universal equation, we are writing it at a location for a transition by keeping certain physical constraints in mind, and it is important to keep that physical argument in mind when we are writing this equation. Next is we can write this, if you are now using the Prandtl's mixing length model, maybe you can write this as rho Lm square now see if you are modeling the flow close to the wall and you are going along the y direction. Now you know that along the y direction u increases, so du dy is positive. Therefore, it is just possible to write it as du dy without going for the mod in this type of a case, right, because here u bar will increase with y from the wall. At the wall it will be 0 because of no slip condition. So that is the first thing that we do by appealing to the physical picture. Now you may also make a simplification by considering that there may be fluctuations in all directions, but the mean flow is like unidirectional with only x component. So then this may be approximately like du dy, with du dy means du mean dy. So whenever we are writing for a turbulent flow, we are writing it for the mean quantity. So if it is that the mean over the other directions is 0, then only we can write it in this way, but otherwise the partial derivative you have to write. No matter whatever you write, you may have to stop here because you do not know what is the mixing length. And see, that is where Prandtl gave another hypothesis. What he said is that this mixing length is sort of proportional to the distance from the wall. What was the physical argument? This term is not at all important at the wall. At the wall the laminar effect is there, that which solely dictates the factor. So at the wall whatever is the turbulent stress, that has to be 0, right, and so when y equal to 0 this becomes 0. As you go more and more away from the wall, it has to be more and more important. So physically this term will be increasing as y is increasing, and a simple increasing law may be a linear law. That is what was the logic of Prandtl, and accordingly see these type of logical thoughts are important, because it is not just a formula that at the end we are going to learn. We are going to learn basically how these famous mathematicians or engineers or physicists try to think in attempting a problem which is a very complicated problem in terms of having a simplistic picture, and that gives a lot of training to even the present generation of how to approach an unknown problem. So that means you can write this as a sort of proportionality constant into y. Again this is a model. So this was another hypothesis of Prandtl following up his mixing length concept. Now with this, if you try to simplify the equation now further, so tau wall is equal to rho into k square y square, and maybe now if you divide tau wall by rho, you should keep in mind that that will give you u tau square. What is the velocity scale, square of the velocity scale close to the wall. So that means you have u tau square is equal to k square y square du dy square. Now you may extract the square root by referring to the proper sign by keeping this positive y axis in mind. So if you do that, you will get u tau is equal to ky du dy. Okay. So now what you may do is you may recall that you have u plus is equal to u by u tau and y plus as y by y tau. So let us try to non-dimensionalize this equation in terms of u plus and y plus. So clearly you can see that this becomes k, you may divide both numerator and denominator by y tau, so it becomes y plus by dy plus, and this is du plus. This u bar you absorb with u bar by u tau, that becomes u plus. Okay. So du plus is equal to 1 by k dy plus by y plus, and if you integrate this you get u plus is equal to 1 by k ln y plus plus some constant say capital A. This tells that at a distance somewhat away from the wall the velocity profile should vary logarithmically, and there are important constants appearing. The constant A will of course depend on many things, but for a wall which is very smooth, from experiments this A came out to be very close to 5. See, this is not an exact picture, therefore the constant should be fitted with experiments. So lots of experiments were conducted, and from all the experiments which have been conducted from that time till now, this value of A for a very smooth wall is a sort of like very close to 5. More importantly, although this parameter might vary according to the roughness of the wall, but this parameter K, or I mean in some books written as kappa, this parameter is sort of universal and it does not vary from one condition to another condition. It is a remarkable thing, and the value of this is roughly is equal to 0.41, which was obtained by a lot of hypotheses and experimentation conducted together by the group of von Karman, and therefore this is given in the honor of von Karman as von Karman's constant. So it is not like a theoretically derived constant, but perhaps nature has created things in that way that no matter whatever is the roughness, no matter how the turbulent structures are distributed, but wherever this law is important, this is known as a logarithmic law, log law. And this law is having this constant kappa, which is sort of universal. So it is like a universal constant, but not a fundamentally derived universal constant, but all the experiments have justified it. Of course, I mean there have been people who argued that it could be 0.39 or 0.4 or 0.42 or whatever, but roughly 0.4 is something which has been obtained from all experiments, and that is one of the very remarkable things.